Welcome to today's custom-tailored deep dive. We're really thrilled to have you with us today. We spend just a massive amount of time throwing around terms like the cloud or, talking about our data floating seamlessly through the ether.
Right, like it's just magic.
Exactly, like it's magic. But today, we're doing something entirely different. We are stripping away the software, the sleek apps, the user interfaces, and we're looking at the tangible, gritty, physical reality of the internet. We're looking at the actual copper cables, the microscopic glass tubes, and the invisible radio waves that physically carry every single piece of your digital life.
It's surprisingly physical when you really get down to it. I mean, we've grown so accustomed to this illusion of a wireless floating digital world that we completely forget there is a massive, heavily regulated global infrastructure of physical material making every single click happen.
Yeah, it's wild. And to guide you through this, we're unpacking a highly detailed set of source materials. Specifically, we're looking at an educational presentation on the physical layer of network communications. This actually comes from Module 4 of an Introduction to Networks course at Sewella Technical Community College.
Which is a fantastic breakdown, by the way.
It really is. So our mission today is to demystify what's actually happening inside your walls and, under the oceans. Just to give you a quick teaser to hook you right away, did you know that a standard Ethernet cable works not just because of the copper inside, but because of highly specific, mathematically calculated twists in those wires?
Yeah, that part is crazy.
Right. If they weren't twisted at precisely different rates, your internet connection would essentially just tear itself apart.
The physics involved in just keeping a signal intact over a few feet of cable is, it's staggering, really. It's brilliant engineering that masquerades as magic.
It totally does. So to understand those twists, we first have to understand what the physical layer actually is. In the famous OSI networking model, which is basically how engineers conceptualize network communications, this is the absolute foundation. Layer 1.
The rock bottom.
Exactly. The physical layer's entire job is to take a complete frame of data from the software layer above it and turn those digital ones and zeros into actual physical energy.
Because, software doesn't actually exist in the physical world. Software is just logic.
Right, it's just code.
Yeah, so when your computer wants to send an email, the software organizes that data perfectly. But that data still has to physically travel across the room or, across the Atlantic Ocean. So the physical layer accepts that organized frame of data and translates it into a series of physical signals.
Okay, signals like what?
Well, those signals might be electrical pulses on a copper wire, or flashes of light in a glass fiber, or even microwave frequencies in the air. It sends them out one single bit at a time. Then, the receiving device's physical layer captures that energy, translates it back into ones and zeros, and hands it right back up to the software.
And what really stands out in the source material is who is actually in charge of making the rules for this layer. Because when we talk about internet software and protocols, we usually talk about computer science groups, right? Like the IETF. But the physical layer is governed by a completely different breed of engineers.
Yeah, you are totally leaving the realm of computer science here and entering the realm of electrical engineering and physics.
Oh, wow.
Yeah, the physical layer consists of electronic circuitry, physical media, and connectors. So the standards are defined by organizations like the IEEE, the ISO, and regulatory authorities like the FCC.
The FCC, really?
Oh, yeah. These are the people calculating the exact chemical makeup of a cable jacket, the precise shape of a plastic connector, and, the maximum allowed voltage of an electrical pulse so it doesn't just melt your hardware.
Okay, let's unpack this, because the source breaks this translation process down into 3 functional areas. It lists physical components, encoding, and signaling. Now, the physical components are obvious to anyone who has ever touched a router. That's the hardware, the network cards, the actual physical cables. But the difference between encoding and signaling that took me a second to wrap my head around. I kind of think of it like a flashlight.
Okay, yeah. Taking that flashlight idea, let's break down the mechanics. The physical component is just the plastic body, the battery, and the bulb of the flashlight itself.
Right. And the encoding is knowing Morse code. It's the agreed-upon predefined pattern. It's you and me agreeing beforehand that a long pulse of light means a dash, and a short pulse means a dot. The source mentions a classic method called Manchester encoding, where a voltage dropping from high to low represents a 0, and a voltage jumping from low to high represents a 1.
Which is very clever.
It is. That is the logical code.
Yeah.
But the signaling is the physical act of my thumb actually pressing the button on the flashlight to generate the energy.
Which is a crucial distinction, Encoding is the logical pattern, while signaling is the physical generation of the voltage, the light, or the radio wave that actually carries that pattern over the medium.
Wait, so if I'm understanding this correctly, the entire internet at its absolute core is basically just an incredibly fast, highly regulated flashlight or buzzer. We're just turning energy on and off.
I mean, when you strip away all the sleek interfaces, yes, absolutely. But what's fascinating here is how mind-bogglingly complex those flashes have to become to support modern network speeds. Because you might wonder, why can't a 1 just be a high voltage and a 0 just be a low voltage?
Yeah, why not keep it simple?
Because of timing. If your computer sends, say, a million zeros in a row, the electrical line just stays at a low voltage for a relatively long time. The receiving computer might completely lose track of exactly how many zeros were sent because there is no visual tick of a clock to keep it synchronized.
Ah, so the line basically looks dead and the receiver just loses its place in the data stream.
Exactly. So complex encoding schemes like the 8B, 10B encoding used for gigabit speeds, they deliberately inject extra transitions. They artificially flip the signal between high and low just to keep the receiving computer's internal clock perfectly synchronized with the sender.
Oh, wow.
Yeah, it's the flashlight analogy, but the person clicking the button is doing it billions of times a second, injecting extra clicks just to keep the rhythm with flawless microscopic precision.
That is wild. Every single time you plug a cable into your laptop, that insane translation process is happening instantly. But, now that we know how these signals are physically created, we run into a new problem. How do we measure if this flow of data is actually performing well? The Sewella module outlines 4 specific metrics for this: bandwidth, latency, throughput, and goodput.
Because generating the signal is only half the battle. If the physical layer is about creating the flow of data, these metrics tell us the reality of how that data actually survives the journey.
I was thinking about this like a massive highway system.
Yeah.
So bandwidth is the fundamental capacity of the medium. It's usually measured in bits per second or megabits or gigabits. In our highway analogy, bandwidth is just the number of lanes on the road. It's purely the potential capacity.
Right. A 10-lane highway inherently has a higher bandwidth than a little 2-lane country dirt road.
Exactly. Then you have latency. That's the amount of time it takes for data to travel from point A to point B.
Yeah.
On our highway, latency is how many minutes the drive actually takes. But then we get to throughput. The source defines throughput as the actual measure of bits transferred over a given time. And it notes that throughput is usually much lower than bandwidth.
Yeah, bring it back to your highway. Throughput is how many vehicles are actually successfully passing a specific checkpoint in an hour.
Okay, that makes sense.
I mean, even if you have a 10-lane highway with massive potential bandwidth, if there is a toll booth or an accident or just heavy congestion, your actual throughput is going to be far lower than your theoretical bandwidth.
And then there is goodput. The presentation calls goodput the usable data transferred over time. It is calculated as throughput minus overhead, and it is always lower than throughput. So if throughput is counting every single vehicle that passes the toll booth, goodput is counting only the vehicles that are actually carrying the specific passengers you care about.
The VIPs, basically.
Right. Goodput ignores all the network overhead. It ignores the delivery trucks carrying road maintenance gear, the police escorts, and the safety vehicles.
And if we look at why this matters directly to you, the listener, goodput is the holy grail. It is the only metric that actually dictates your personal user experience. Your internet service provider is always going to advertise a massive bandwidth.
Oh, always. Up to 1 gigabit.
Exactly. They're selling you the theoretical 10-lane highway. But after you account for network congestion, lowering the throughput, and then subtract all the data formatting, the error checking, and the protocol overhead, the goodput is what is actually left over to load your web page or stream your movie.
So when my 4K video starts buffering, I shouldn't be yelling at my screen about my bandwidth. I should be yelling about my goodput.
You should definitely be yelling about your goodput.
No.
And the friction causing that drop in goodput usually comes down to the physical medium itself, which brings us to the actual materials these highways are made of.
Right. Historically and honestly still dominantly inside our homes and office buildings, the absolute king of the physical layer is copper cabling.
Oh, for sure. Copper has dominated for decades for a few very practical reasons. It is relatively inexpensive, it is highly flexible so you can run it through walls easily, and it has incredibly low resistance to electrical current.
But because it relies on electrical pulses, it has severe physical limitations. The source mentions attenuation, which is basically a fancy way of saying the electrical signal literally runs out of energy and degrades over distance.
Yeah, it just gets tired.
And then there's interference. Copper is highly susceptible to EMI and RFI, electromagnetic interference, and radio frequency interference. We're talking about invisible disruptions from fluorescent lights, microwaves, and electric motors. Plus, there's crosstalk, which is signal bleed between adjacent wires inside the very same cable.
It's a hostile environment in there. So to fight those forces of physics, engineers have iterated on copper cable designs over the years. The source touches on coaxial cable, which has a heavy metallic shield to block interference. Then there's STP, or shielded twisted pair.
I've seen that one. It's pretty bulky.
Yeah, STP wraps every pair of wires in foil and then wraps the whole bundle in a metallic braid. It offers incredible protection against noise, but the engineering trade-off is steep. It's expensive, it's stiff and hard to install, and it requires meticulous electrical grounding.
Grounding? Why does it need that?
Because if you don't ground an STP cable perfectly, that metallic shield actually acts like a giant antenna and pulls ambient radio noise directly into your data stream.
Oh, wow. So the shield becomes a weapon against you. Which brings us to the absolute workhorse of the modern network UTP, or unshielded twisted pair. This is the standard blue or gray Ethernet cable with the plastic RJ45 connector that you probably have sitting on your desk right now.
Yep, the classic.
And it's categorized by bandwidth potential. You've got Cat5e handling 1 gigabit per second, Cat6 handles up to 10 gigabits, and Cat8 can push 40 gigabits. But here is my question. It's literally called unshielded.
It is.
If it doesn't have a foil shield and it's carrying sensitive electrical pulses, aren't we just asking for our data to be scrambled by the microwave in the office kitchen? Why is an unshielded cable the global standard?
I know it sounds completely counterintuitive to just remove the armor, right? But this is where the sheer genius of electrical engineering comes in. UTC doesn't use physical shielding. It uses the laws of physics to protect itself. Specifically, the principle of cancellation.
Cancellation.
Yeah. When you run an electrical current through a copper wire, it naturally creates a small circular magnetic field around that wire. By pairing two wires together in a circuit and sending the exact same signal but electrically inverted, their magnetic fields become exact opposites.
So they fight each other.
They literally cancel each other out. And in that process of canceling their own fields, they also reject external noise like EMI.
Okay, here's where it gets really interesting. Because if you strip the jacket off a UTP cable, you'll see 4 pairs of color-coded wires. The source mentions they rely on a second technique, varying twist rates.
This is the detail that feels like magic to me. If you have 4 pairs of wires running parallel inside a cable, and they were all twisted at the exact same interval, their magnetic fields could eventually align over a long distance and cause crosstalk. Basically, they would bleed into each other.
Because the patterns match up.
Exactly. So engineers follow hyper-precise specifications to twist each pair a different number of times per meter. The orange pair might have 72 twists per meter, while the blue pair has 65. By constantly varying the twist rates, they ensure the magnetic fields never accidentally sync up.
So you have these opposite magnetic fields actively canceling each other out, and then you mathematically offset their twist rates to ensure they never accidentally resonate. That is an incredible cost-to-performance triumph. You get all the protection of a shield without the cost or stiffness of actual metal foil.
It's so elegant.
It really is. Now, the source also brings up an older networking headache straight through versus crossover cables. I remember years ago having to carry a specific crossover cable just to connect 2 laptops directly together. Why did we have to do that?
Because historically, physical network ports were rigidly mapped. Pin 1 and 2 were always for transmitting data, and pin 3 and 6 were always for receiving. If you connected 2 laptops with a normal straight-through cable, the transmit pin on laptop A was wired directly to the transmit pin on laptop B.
So they were both shouting into the same pipe, and nobody was listening to the receive pins.
Exactly. It's like 2 people talking over each other on the phone.
So a crossover cable literally crossed the copper wires inside the plastic jacket, physically routing the transmit from device A to the receive of device B.
Precisely. But today, network cards feature a technology called Auto MDIX. The hardware is now smart enough to instantly detect which pins the other device is transmitting on, and it dynamically reassigns its own pins internally in a fraction of a second. So the physical crossover cable is essentially a museum piece now.
Well, good to know I don't need to carry one anymore. But, you know, as brilliant as copper engineering is, it hits a hard physical wall. No matter how you twist it, an electrical signal in copper degrades completely after about 100 meters. Copper is fantastic for getting from your desk to the server room down the hall. But what happens when we try to push maximum goodput over a massive distance? How do we connect a server room in New York to a data center in London?
You just can't do it with copper. The medium itself becomes the bottleneck. We have to completely abandon electricity. We have to use light.
Light. This is the leap to fiber optic cabling. Instead of a copper wire, you're using an incredibly thin, highly purified strand of flexible glass. The core of a fiber cable is often not much larger than a single human hair, and instead of pulsing electrical voltage, your bits are encoded as flashes of light.
Which is mind-blowing when you think about the scale. And because it's using photons instead of electrons, the presentation notes that fiber is completely 100% immune to all that EMI and RFI interference we just talked about.
It doesn't care about magnetic fields or microwaves at all.
Not even a little bit. And the way it keeps the light inside the glass is through a physical phenomenon called total internal reflection.
Right. The glass core is surrounded by a slightly different type of glass called the cladding. Because they have different refractive indexes, the cladding acts like a perfect mirror. When you shoot light into the core, it bounces off the cladding walls and travels down the cable without escaping.
It's essentially a microscopic hall of mirrors.
So cool. Now, the source outlines two main types of fiber media, single-mode fiber, or SMF, and multi-mode fiber, or MMF, and the difference basically comes down to the size of that core.
Right, so single-mode fiber has a microscopic core only 9 micrometers wide. Because it's so tiny, it requires expensive, highly precise laser technology to shoot a single straight path of light down the center. Multimode fiber, on the other hand, has a much wider core. It uses cheaper LED technology instead of lasers, and because the core is wider, it allows multiple light rays to enter at different angles and bounce along different paths.
I was picturing multimode versus single mode, like a hallway. Multimode is like taking a handful of bouncy balls and throwing them hard down a wide, mirrored hallway. They're going to ricochet off the walls all the way down. The problem is, because they're bouncing at different angles, they take different path lengths.
Oh, that's a great way to picture it.
Thanks. So the balls you threw at the exact same time will arrive at the end of the hallway at slightly different times. Over short distance, that's fine. But over a long distance, the pulses of light start blurring together.
And that blurring is called modal dispersion. It is exactly why multimode fiber is only used for shorter distances, like connecting servers within the same building.
Makes sense.
Single-mode fiber, on the other hand, is like taking a high-powered laser pointer and shooting it perfectly straight down a microscopic tube. There's no bouncing, no dispersion. All the light arrives at the exact same time, which allows single-mode to carry data for dozens of miles without losing integrity.
That perfectly explains the deployment types the source mentions. We use multi-mode for enterprise networks inside buildings, but we rely on single-mode lasers for long-haul networks connecting cities, and those incredible submarine cable networks surviving the crushing pressure at the bottom of the ocean. The source also mentions fiber to the home, or FTT. Why go to the immense expense of running fragile glass directly to a consumer's house?
Well, if we connect this to the bigger picture, fiber to the home is a paradigm shift in reliability. With copper infrastructure, your internet speed is heavily dictated by how far your house physically is from the provider's neighborhood node. The longer the copper, the weaker the signal.
So distance really punishes you.
Exactly. Plus, older underground copper lines are susceptible to water damage and electrical interference. Fiber has near zero signal loss over those neighborhood distances and absolutely zero electrical interference. By replacing the finest stretch of copper with glass, you completely eliminate the physical friction that degrades your goodput.
The trade-off, of course, is that glass is much harder to work with. You can't just snip a fiber cable, strip it with a pocket knife, and crimp a plastic end onto it like you can with a copper Ethernet cable.
Definitely not. Don't try that.
No. It requires specialized fusion splicers to physically weld microscopic strands of glass together perfectly.
Which is precisely why copper remains the king of the local office network, while fiber rules the global backbone.
All right, so we've built these perfect glass and copper highways. We understand the cancellations, the twist rates, and the lasers. But if we're being completely honest, you're probably listening to this deep dive right now on a device that isn't plugged into anything at all. You are mobile. So what does this all mean? What happens when there is no physical wire?
Wireless. This brings us to wireless media. It is the third way to connect to the physical layer, and it uses electromagnetic signals, specifically radio or microwave frequencies, to represent the binary data in open air.
The presentation lists a few major standards. There's Wi-Fi for your standard local networks. There's Bluetooth for short-range personal connections, like, pairing your headphones. And there's Zigbee, which is specifically engineered for low data rate, low power devices like battery-operated smart home sensors that only need to send a tiny pulse of data maybe once an hour. To make a standard Wi-Fi network work, you need a wireless access point to bridge the radio waves to the wired network, and a wireless antenna inside your device.
And, it's worth noting that the blinking plastic box your internet provider gave you is actually a combination of devices. A modern home router is a router, a wired switch, and a wireless access point all crammed into a single shell.
It does it all.
Uh,
But as magical as wireless mobility is, it comes with severe physical compromises. The module highlights a few major limitations. First is coverage area. Building materials, brick walls, and even the terrain of your house absorb and deflect radio waves.
they're very fragile in that sense.
Yeah. Second is interference. Because you're blasting data into shared airspace, your signal can be scrambled by your microwave oven, a baby monitor, or just your neighbor's router screaming on the exact same frequency channel.
And this raises an important question about the trade-offs we inherently accept for mobility, because the third limitation is security. With copper or fiber, an attacker literally has to physically splice into your cable to steal your data.
You need physical access.
Right. But with wireless, your private data is bouncing off the walls of your living room, passing through your windows, and floating out into the street. Because the physical layer is completely uncontained, we have to rely entirely on heavy encryption at the higher software layers to keep it safe.
Wow, yeah. But the fourth limitation is the one that really caught my attention. The source states that wireless is a shared medium, operating in half duplex. What does that actually mean for performance?
Half duplex means a wireless device cannot transmit and receive data at the same time. It can only do one or the other. And because it's a shared medium, only one device on the network can transmit at any given microsecond.
Oh, wait. I picture it like a crowded dinner party. If everyone tries to shout their stories at the exact same time, it just becomes unintelligible noise. The data collides. So to have a conversation, only one person can speak at a time while everyone else listens.
That is exactly right, and it perfectly describes the protocol Wi-Fi uses to manage this. It's called CSMSA. It stands for Carrier Sense Multiple Access with Collision Avoidance.
It is quite the acronym.
It is a mouthful, but the mechanism is surprisingly polite. It literally translates to listen before you talk. Before your phone sends a piece of data over Wi-Fi, it quickly listens to the radio frequency. If it hears your smart TV currently transmitting data, your phone backs off, waits a random number of microseconds, and tries again.
Wait, really? So if I have my laptop, my phone, a smart TV streaming 4K, and a smart thermostat all connected to my Wi-Fi, they aren't actually talking to the router simultaneously. They're constantly pausing, waiting in line, and taking microscopic turns speaking.
Precisely. It happens so fast that it feels simultaneous to you. But physically, they are taking turns, which means the more guests you add to the dinner party, the more smart devices you add to your Wi-Fi, the less speaking time everyone gets. Your overall throughput plummets.
So if you want true, uncompromised performance, a wired connection is still vastly superior. If I plug my computer directly into the router with a Cat6 copper cable, it gets a dedicated, full duplex lane on the highway. It can send and receive massive amounts of data simultaneously without ever having to wait for the smart thermostat to finish talking.
From a purely physics-based perspective, yes, wireless gives us unparalleled world-changing mobility. We couldn't live without it. But the laws of physics dictate that a dedicated copper wire or a perfectly mirrored glass fiber will always be a significantly more robust, higher-capacity medium than open air.
So if you're ever getting frustrated with lag during an important video call and you're pacing around on Wi-Fi, it might be time to dig out that blue Ethernet cable and rely on the magic of magnetic cancellation.
You can never go wrong trusting the copper.
This has been an incredibly eye-opening journey. We have completely bypassed the software to look at the reality of the physical layer. We explored how engineers translate digital bits into physical energy and why tracking goodput is the only way to measure our true experience.
Yeah, that goodput is key.
We unraveled the brilliant mathematically varying twist rates inside everyday copper cables that actively cancel out interference. And we explored how entirely eliminating electrical friction by bouncing lasers down microscopic glass tubes allows us to connect continents. And finally, we unpacked the incredible convenience and the shared medium bottlenecks of the radio waves beaming around your living rooms.
I really hope that the next time you glance over at the blinking lights on your home router, you see it a little differently. It's not just a plastic box providing internet. It is a hyperactive nexus point. It is a place where billions of carefully encoded electrical pulses, laser light waves, and radio frequencies are being physically generated, translated, and routed in real time, all while perfectly avoiding collisions. It is an absolute marvel of physical engineering.
It truly is. And it leaves me with one final thought to mull over. We have pushed the physics of copper, glass, and radio waves to their absolute limits just to send our digital ones and zeros faster and faster. But as our global hunger for data continues to explode exponentially, what entirely new, unimaginable physical medium might engineers have to invent next to carry the internet of the future? We'll leave you to think about that. Thanks for joining us on this deep dive.